in your attendances in the chat. All right. So today I plan to start with an example of small oscillation, an example of things that you might encounter in different examinations. So the thing I want to discuss is called the linear triatomic molecule. Triatomic molecule. Okay. So we will describe the small oscillations in this molecule. And find out the vibrational degrees of freedom. So to represent it diagrammatically, suppose basically you have a central molecule of a mass, certain mass, and it is bound to two other molecules of different masses. So here one, and let's say the other is in this direction. Okay. So the mass of these red molecules are m1, and the mass of the central molecule is m2, and the spring constant for the springs are k. So k is basically the spring constant. So if you are looking for a more concrete examples, you can think about the CO2 molecule. So if you check the CO2 molecule, so this is an example of a linear molecule. So the carbon and oxygen bonds are kind of aligned in a straight line. So this thing is constitutes a linear molecule, and you can identify this to be your carbon atom, and towards the end these are your oxygen atoms. Okay? And this is basically the covalent bonds. And the bond lengths can change with a spring constant K. Okay. Now, what I have done is to show that so this is, suppose this is the equilibrium position of the molecule, and in general, when this molecule oscillate, uh, so this is the molecule in one dimension, and this is suppose your x-axis. So from the equilibrium position, we say that this m2 is shifted by an amount x2, okay. And this one is shifted by amount x1, and this one is amount shifted by, like, the displacement along the x-axis for these three molecules are x1, x2, and x3 respectively. Okay. So the potential energy, that is basically k times the deformation of the spring. So if, for example, look at the spring on the left. So if you look at the spring on the left, and if this is shifted by x1, this is shifted by x2, the net deformation would be x1 minus x2, right? The difference between x1 and x2. So I can write down the potential energy to be for the left hand side spring to be half k x1 minus x2 whole square, and for the right hand side spring it would be half k x2 minus x3 whole square. All right. And of course T is basically the kinetic energy of all those masses, so half m1 x1 dot square plus m2 x2 dot square plus m3. So this one is also m1 actually. m1 x3 dot square. Okay. So the Lagrangian would be given by t minus b for this kind of a conservative system. So it is basically half m1 x1 dot square plus m2 x2 dot square plus m1 x3 dot
Excuse me,
square. Yes, tell me.
sir. While writing the kinetic energy, we usually like used to take the total time derivative of um, uh, the generalized coordinate, right? And here, like x1, x2, x3 are displacements from their respective mean positions.
Yes, these are still generalized coordinates. There is no constraint in this system. I'm not saying that the bond length is fixed. There are no constraints.
Okay, so like displacements can be like in the same way treated as the fixed the coordinates.
Yes, yes. These three are just independent displacements.
Oh, okay, sir. Now,
Okay. So all of them can be displaced independently. All right. So half k x1 minus x2 whole square minus half k x2 minus x3 whole square. Great. So now you can write down the equation of motion, for example. The equation for motion for corresponding to x1 would be given by del L, rather I just put d dt of del L del x1 dot minus del L del x1 equals 0. So if you do that for x1, you get the equation of motion to be this. So m1 x1 double dot plus k x1 minus k x2 equals 0. Now, so this is for x1. So this is the equation of motion for this one. For x2, you can similarly write down. It would be m2 x2 double dot, if I am doing it correctly in my notes, minus k x1 plus 2k x2 minus k x3 equals 0. And for x3, it would be given by m1 x3 double dot minus kx2 plus kx3 equals 0. Now, just rearrange these equations a bit to rewrite this here. So I am basically abbreviating, say nu 1 square equals k by m1 and nu 2 square equals k by m2. So I define these two quantities. I divide these equations by m1 and m2 respectively. And then what I should get is x1 double dot plus nu 1 square uh, x1 minus nu 1 square x2 equals 0. Hold on a second. All right. And then x2 double dot minus nu 2 square x1 plus 2 nu 2 square x2 minus nu 2 square x3 equals 0. And x3 double dot minus nu 1 square x2 plus nu 1 square x3 equals 0. So these are my simplified form of the equations that I get. Okay. Let me add another page here. So now it's time to put in our trial solution. So I would just say that these things oscillate with a frequency omega. So what I assume is that the solution will be given by xt equals equivalent to the column matrix of three elements x1t, x2t, x3t, which is equals to given by the time dependent part is taken out by the oscillatory behavior, and I will denote it as compactly as it a e to the power I omega t. Remember this a is a column matrix. Okay. Uh, so now if we substitute this trial solution into here, then you can rewrite the things as, so I would just write it down in the form of a matrix minus omega square plus nu 1 square. Whenever there is a double derivative, minus omega square will come, minus nu 1 square, 0 minus nu 2 square, minus omega square plus 2 nu 2 square, and minus nu 2 square, and 0 I think minus nu 1 square minus omega square plus nu 1 square, and then a1, a2, a3, oops, equals 0. So this will be your form of the equation in terms of a1, a2, a3. So for non-trivial solution for a1, a2, and a3, you will just say the determinant of this matrix would be 0. So the determinant of this matrix should be 0. Now, if you do that, from that you find the roots of omega. So find the roots of omega square, and if you do it, you will find omega 1 square to be equals 0, omega 2 square equals nu 1 square, and omega 3 square equals nu 1 square plus 2 nu 2 square. Okay. So these are the three normal frequencies that you have for the modes of oscillation. So these are your normal frequencies. So I call these my normal frequencies. Okay. Now again, to find out the column matrix A for each of these normal frequencies, right? Now we have to find out to find the normal modes of oscillations. So let me write down. So to find the normal modes of oscillation, we need to find A corresponding to each omega I square. Okay. So if you want to find out for omega 1, let's say, so for, let me, number 1, omega 1 square equals 0. So for that, so how would you find that? So basically, you will put omega square equals 0 here, okay, in this equation here. So put the value of omega square. All right. So if you put the value of omega square here, you will see that you get a1 equals a2 equals a3. I mean, uh, just put it here. If this is 0, then this is just nu 1 square minus nu 1 square. So basically it tells you a1 minus a2 equals 0. So from the first, let me do it for you if you are not getting it. 0, and put in the other thing also. And then a1, a2, a3. this should be equal 0. So you multiply this with this one, you get A1 minus A2 equals 0. That implies A1 equals A2. And from this one, the last one, you will also get A2 equals A3. So finally, what you will get for this solution, you will get A1 equals A2 equals A3. Okay. So this is very much like the eigenvector equation. So remember, in the eigenvector equations, you do not uniquely find the vector, because the magnitude of the vector is still undetermined. Okay, so you have to later normalize those eigenvectors. So um, what the eigenvalue equation does is that it gives you an interrelation between the components of the vector. It does not specify the length of the vector, at least for non-degenerate cases. Okay. Now, so once you have that, you call the common eigenvalue to be, let's say, if you want to normalize this thing, so then you just put it, all of them equals to 1 by root 3, then you can check that a1 square plus a2 square plus a3 square equals 1. Okay, if you want to normalize it, but it is seldom necessary. So you do not need to normalize it, but you need to remember that all the displacements are equal in this case. Okay. Now, what does it imply in the context of the actual oscillation? For certain scenarios, you can easily visualize these modes of oscillation. Okay, so my molecule look like this. Oops. So this, remember what were these A1, A2, A3? These were the displacements for x1, x2, x3. So the displacement, the amplitude of oscillation for x1 is A1, the amplitude for oscillation of x2 is A2, and amplitude for oscillation for x3 is A3. Okay, so these were my amplitude corresponding to each of those displacements. Okay, and x1, x2, and x3 were associated with the displacement of the three molecules. So it tells you that all the displacements or all the amplitudes should be in phase and should be equal to each other. So if this is moved by 2 centimeter, then this should be moved by 2 centimeter as well, and this should be moved by 2 centimeter. 2 centimeter is too large. Let's say 2 micrometer. Okay. So the displacements are equal. That means the molecule is basically being translated as a whole. Okay. So that's why there is no oscillation involved. Like you are basically translating the molecule, and that's why the oscillation frequency is 0. So it's not an oscillation, it's an overall translation. Okay, so let us investigate the second possibility, which is omega 1 square equals nu 1 square. So the second possibility is omega 1 equals nu 1 square. So again, if you play the same game, you substitute omega 1 square equals nu 1 square um, in your equation. Sorry, not omega 1. I should put it omega 2 square equals nu 1 square. Second frequency. So then you will have A1 equals minus A3. Okay, and A2 equals 0. Now again, draw that molecule, and let us try to see what is happening in here. All right. Now, so now I got that A2 equals 0. That means the central molecule is fixed. It doesn't go anywhere. It is just fixed in there. Okay. And A1 equals minus A3 means if this fellow moves the 1 micrometer in this direction, then this one should move 1 micrometer in this direction, because they are in the opposite direction. Their movement is in the opposite direction because of this minus sign. Okay. So now you see basically there is two independent vibration about the, so this central molecule is fixed here, and basically each spring vibrates with its own mind, and since the spring constant is k, you imagine the oscillation frequency would be square root of k by m, which is precisely equals nu 1. Okay, so there is no surprise at all. So the second mode is is nu 1 square. All right. And the third mode can be a bit more complicated. So the third mode,
Sir, you have shown that that in molecules are moving towards them. It can also happen they are moving away from them.
yes, of course, but it's the same thing, right?
Okay.
I mean, when it oscillates, basically it says that this and this point are at the opposite phase. When this moves in this direction, this has to move in this direction, and when this moves in that direction, it has to move in that direction. That's it. So it's, you can imagine that this one is fixed, and the two molecules, the two other atoms are vibrating independently. Okay. Not precisely independently, but those are vibrating with frequency given by this k over m. Okay. Now the third mode is omega 3 square equals nu 1 square plus 2 nu 2 square. So what you have here, so if you calculate, then this would be a bit complicated. So this will give you a1 equals a3 and a2 equals, if I am right, minus 2m1 by m2 times a1 or a3. Okay. So you see this is kind of a composite vibration. This is not as simple as the other two. Okay. So this means that uh, if the end atoms move in this direction, then the central atom will move in the opposite direction with the ratio determined by the masses of those things. Okay. So it's difficult to interpret, but this is another eigenmode of frequency. That this is another eigenmode of vibration. So these are the three normal modes of vibration. Now, if I try to find out my normal coordinates, uh, I can easily find it out by this, in this way. So suppose, so I will consider the scenario when m1 equals m2. You can also find out the general scenario here. So m1 equals m2 means in this case, so this relation will be a2 equals minus 2a1. Okay. That is the scenario that I will be concentrating on. Okay. So remember, so then the general solution would be a linear superposition of the three modes of vibration. So one mode is e to the power I omega 1t. Okay. Plus another mode is e to the power I omega 2t, plus another mode is e to the power I omega 3t. So this is my general solution. Sorry, forgot to write down the column matrix. So if I put, so remember for the first mode of oscillation, I have in all the things, a1 equals a2 equals a3. So I have basically 1, 1, 1 here times some normalization, that is n1. Okay. For the second mode, I had 1, 0, minus 1 here times some normalization constant n2. And for the third mode, I have 1, 1, minus 2 here plus some normalization constant, say n3. Okay. So this is my mode, but remember this xt is basically a three element column matrix, so x1, x2, x3. All right. So this is it. So that means if you split it up, that means x1 equals n1 e to the power I omega 1t plus n2 e to the power I omega 2t plus n3 to the power I omega 3t. x2 equals to n1 e to the power I omega 1t minus 2n3 a to the power I omega 3t. There is no n2 here, and x3 will be given by n1 a to the power I omega 1t minus n2 a to the power I omega 2t plus n3 a to the power I omega 3t. So now if I want to find the normal coordinates, so first one of the normal coordinates I can easily write down as, say, xi1t, and it would be just x1 plus x2 plus x3. Okay. So if you do x1 plus x2 plus x3, you see that this one cancels out, and this cancels out. You are just left with kind of 3n1 times e to the power I omega 1t. Now, xi2t similarly would be x1 minus x3, and that would be given by 2n2 e to the power I omega 2t, and xi3t will be given by x1 minus 2x2 plus x3, and if you calculate, it would be 4n3 to the power I omega 3t. So notice that the normal coordinates are the linear combination of the original coordinates. Okay. So these are the linear combination of the original coordinates, and this vibrates with a purely with frequency omega 1. This is purely frequency omega 2, and this is frequency omega 3. Okay. So you use these coordinates. Actually, you normalize the transformation usually. So you use these coordinates, this xi1, xi2, xi3. It is easier to use because in terms of them, the Lagrangian will be much simpler. Okay, so so the way it looks. All right. Now, in terms of xi1, xi2, and xi3, basically my Lagrangian breaks down into three independent modes of vibration. Okay. So suppose you are solving the quantum mechanical problem of, say, linear triatomic molecule. Let's say carbon dioxide, like this. You know the masses of the carbon and the oxygen atom, and your Lagrangian is this, means your Hamiltonian is also very complicated. Now, if I ask you to solve the Schrodinger equation in terms of this x1, x2, and x3, it would be complicated because there will be cross term, let's say, which will be given by x1 and x1 times x2. So here there will be cross terms like x1, x2. Here there will be cross terms like x2, x3. You do not know how to solve the quantum mechanics with this kind of coordinates. This is very complicated. So what you do is that you change your coordinates from x1, x2, x3 to xi1, xi2, xi3, and then your Lagrangian or your Hamiltonian would be simplified, or rather, let me say the potential would be simplified, and it would be given by half omega. I might be missing some constants here. Xi1 square plus half omega 2 square xi2 square plus half omega 3 square xi3 square. So if you remember the exercise for the general formulation of the small oscillation problem. So in terms of xi1, xi2, xi3, it's much easier to solve the problem. So that's why when we try to solve the quantum mechanics of these kind of complicated molecules, we try to find out the normal coordinates first, and then we solve the quantum mechanics in terms of those. So you might remember from your old atomic physics days that if I say that there are three atoms moving in one dimension, then there are 3 degrees of freedom. Okay. So there are 3 degrees of freedom. Yeah, this guy has. Now, if you break it down, these 3 degrees of freedom, one is overall translation. You translate the molecule overall. So basically, one translational degree of freedom. Since this is motion in one dimension, so there is no rotation involved, at least not in a distinguishable way. Then the other two will be vibrational degrees of freedom. Okay. So, and that's what we found. There are one translational degree of freedom and 2 vibrational degrees of freedom. And perhaps you have been dealing with these vibrational energy levels of these molecules. Okay. So remember this vibrational spectra are really closely spaced. I don't know if you have been taught these things in your bachelor's day or not, but let's say there are vibrational spectra of molecules. So the vibrational spectra of molecules. So there you have learned, perhaps you have only did diatomic molecule. So diatomic molecule is simple, it's just one translational and one vibrational. So the vibrational frequency is very simple. Okay, but for complicated molecule like this, or even more complicated molecule, you know that these labels, so these labels are separated by a tiny amount, and since these are harmonic oscillators, these are harmonic vibrations, the separations would be given by h cross times omega. But what is the value of this omega? This omega would be equal to the vibrational frequency. Now, what is the vibrational frequency for such a complicated molecule? There is no single vibrational frequency of that molecule. Okay, there are many of the vibrational frequencies, and those vibrational frequencies are precisely this: omega 1, omega 2, and omega 3. Okay, so so these are your vibrational frequencies, and your quantum mechanical levels are spaced according to these things. So that's when your these calculations actually comes in very useful when you try to analyze the quantum mechanical behavior of such a system consisting of triatomic molecule or so on. So I will pause for a moment and I will see if there are any questions for this.
Sir,
Yes.
sir, what is the general rule of getting this xi1 from that x1s or
Basically,
or
basic,
x? Yeah.
basically you have to invert the matrix. So you see, I have written x1. Basically, you solve xi1, xi2, xi3 from
Oh,
those
okay,
things.
okay, okay. Got it, sir. Got it,
Okay.
got it.
Okay. So from here, you will be able to see.
Yes, sir.
Um, or if you want to play by the general rule, then I have described the general method for obtaining these xi1, xi2, xi3 by first normalizing these things and then defining in a certain linear combination. In the previous class I mentioned that you can do that, but that is not very often necessary. You can get it from intuitions, like what will be the linear combination. But if you are in completely in a blind situation, you do not get any intuition from this, then you follow the recipe that I described in previous class. Okay. Towards the end, I described how you can find your normalized coordinates, or yeah, normal coordinates. It should be clear there.
Yes, sir.
Actually, if you see my notes, there should be a homework at the end of this. If you do that homework, then it should be clearer. Okay. All right. Any further questions? All right, then let me move on to the next topic. So next I want to start talking about Hamiltonian, but I think today might not be a good time to introduce it completely. So let me do the precursor for that Hamiltonian. So let me talk about something called the Legendre transformation. So the Legendre transformation is basically a transformation between its coordinates and the partial derivatives, like what you want to keep it as your explicit variable. So Legendre transformation gives you sort of a control or sort of a handle to treat as explicit variables the things as you wish. Okay. To give you an example, suppose to start with, suppose f is a function of three variables x, y, and z. Okay. Then df would be given by del f del x dx plus del f del y dy plus del f del z dz, and there can be more variables, and you will keep adding things on here. Okay. Now let me abbreviate the notations a bit. So I will call del f del x to be capital X, del f del y to be capital Y, and del f del z to be capital Z. Okay. And now I want to construct a function where the explicit variable is not x, not my small x, but the derivative of f with respect to small x, which I'm denoted by capital X. So I want to switch between these two. So let's say small x and capital X. So I want to construct a function g, which is no longer an explicit function of small x, but an explicit function of capital X and y and z. Okay. So I just replace small x by capital S, and I want to have that. So the prescription is that you can do that if you subtract from the original function the old variable times the new variable, which is the derivative of that thing. So now you should be able to check that if you calculate now dg, which is equals df equals df minus x dx plus x times dx. Now remember, what is this df? So df is given by x dx plus y dy plus z dz and minus this. So these two will cancel out, and you should be left with this is minus x dx plus y dy plus z dz. Okay. So you see that the explicit variables are capital X, small y, and small z. Okay. So now if you identify this thing as del g del x dx plus del g del y dy plus del g del z dz, you get an interesting relation saying that so this quantity del g del capital X would be your minus x. Okay. and since you did not do anything with the y and the z part, so it stays the same as for the f functions. So del g del small y still equals to capital Y, and del g del z equals capital Z. Okay. Now you can probably want to now replace, let's say, this y with small y. Okay, so this y would be replaced by this small y. So now you want to create another function, let's say h, that would be a function of capital X, capital Y, and small z. So what you do is that you start with g x small y small z and subtract from it simply capital Y times small y. Okay, and you have things like that, and so on. So you kind of get the idea what I am trying to do here. So what I am doing here, that I am saying that my explicit variables are being modified as I wish. Okay. So now, first of all, you should notice that if you do two consecutive Legendre transformation of the same nature, then you get the same function back. For example, suppose you had gxyz here. Okay. Now, if you want to do again a Legendre transformation with that, then so what is this? Let me put it. So this was x times this x was del f del x, right? So this is x times del f del x. So this was f x y z minus x times del f del x. So that is the strategy I am doing. So I want to replace x with del f del x. So I am just doing this. Now suppose I have now g x y z, say capital X y z, and I want to construct from this the old function, not f. I just call it, I just give it a different name. What, I am running out of notation. So let me call it, say, a of x, y, z. Okay? I will want to revert back to the to a function which had x as the explicit variable. Now I will do that by doing g, x, y, z minus the explicit variable, that was x, times del g del x. So that should be my strategy here. So in the same, so if you compare with this, this is my strategy. That's small x is replaced by capital X. All right. Now remember, what was this g? So g was f minus capital X times small x. And this is minus x, and del g del capital X, if you remember, that is minus of small x here. This is minus of small x. So x times minus of small x. So these two cancels out, and you are basically obtaining the old function as you expect. So two consecutive Legendre transformation on the same set of variables would do nothing essentially. It will give you back the original function as you would expect. Right. Now, the thing is that you have been doing this thing for quite a while without perhaps realizing that what you are doing is Legendre transformation. For example, you know, in thermodynamics, the thermodynamic potential. So let me give you an example. So if you go back to your lessons of thermodynamic potentials, then you had this thing. So you wrote from the first law of thermodynamics, maybe first and second law, minus PdV. Okay. So this is your internal energy, and the internal energy you wrote as a function of S and V. Okay. Now, from this, basically you relate this thing to your del U del S when V constant, and minus P would be your del U del V when your S is constant. So you get these two relations, right? So T equals del U del S and minus P equals del U del V. Okay, you wrote that, and you considered U to be S and V. Okay. Now, you want to construct a function f, let's say, which will be a function of V, but you want to replace this S, the entropy, you want to replace it with the derivative, that is with T. So you want to replace the function with T and V. So that you should do by, first you say USV minus the original thing S times the derivative, that is del U del S, that is basically T. So this is basically U minus TS or U minus ST, and you know this function by the name of Helmholtz free energy, I guess. Helmholtz free energy. And now if you do the same exercise, then you will find that you get two new relations basically. So if you compare with this thing, since you are not doing anything with the v variable, so you still get p equals minus del f del v when t is constant, but now you will get s equals, so the old variable s, and if you compare with this, the old variable was x. Okay, so if you compare that with s would be minus del f del t when v is constant. So you get these two new thermodynamic equations that that is the explicit variables are now v and t. So basically, so there are two more thermodynamics potential that are known as the Gibbs free energy and the enthalpy, which is H. So those are basically explicit function of complementary sets of variables. So you basically have S, V, T, and P as your explicit variables. So depending on the processes that you are considering, the thermodynamic processes that you are considering, sometimes your volume is constant if that is an isobaric process. No, your pressure is constant when it is an isobaric process. Okay, your perhaps if the isothermal process, the temperature is constant. So depending on which kind of process you are considering, it might be useful to consider one or the other thermodynamic potentials for that particular process. So you judge that by looking at what are the explicit dependents, what are kind of the explicit variables that my thermodynamic potential depends on. So this was an use for the Legendre transformations that you have been using for a long time, perhaps. So we would be doing the same kind of thing for constructing Hamiltonian from the Lagrangian formulation in the next class. Okay. So I will stop today's class here. Now tell me if there are questions. Any questions?
No.
All right. So I think so I will take it as the things are clear to you and not the other way around. So anyway, so I will stop recording now.